Good morning, everybody. Tomorrow we will derive equations for other kinds of problems. So far we just studied as far as the differential equations are concerned, we just looked at the 1D elasticity problem, right? So far 1D elasticity. However, there are many other kinds of problems that can be solved using finite element analysis. And of course, right now we are talking about 1D problems only. Okay. So the first thing, of course, the elasticity problem that we are familiar with. There are other kinds of problem that we will solve is heat conduction problem. Yeah, Aswin.
Sir, sorry to
Yeah,
interrupt.
Aswin.
Sir, sorry to interrupt, but you have not posted the assignment, right? Homework.
Not yet. So today I will do. Okay.
Okay, sir. Thank you.
You were not present yesterday in the tutorial.
No, sir, I couldn't.
So I talked about it. Okay, so we have a heat conduction problem, diffusion problem. Okay, so diffusion will have different kinds of plus. It may have the diffusion for advection, with advection as well. So we will look at the equations, what kind of equation we get out of them. Okay. When we talk about the heat conduction, let us see, you know already that in 1D problem, there may be a bar and there may be some temperature difference, as you know, like if you have T1 here, T2 here, and because of that, what you call your Fourier law, right? Fourier law of heat conductivity, heat conduction. And you give Q, you must have remembered Q is equal to K times A, then T1 minus T2 over L, right? So this you may remember from your high school. However, in a differential format, the Fourier's minus K dt over dx. So where K is what is called is thermal conductivity, and Q is also known as the heat flux. And dt over dx is the thermal gradient, right? So for this,
pardon sir, Ka dt by dx. Oh, I'm sorry.
Yeah, minus K dt over dx.
Okay.
Yeah. Okay. So for the same problem, we are going to derive equation for heat conduction. And like always, what is given here is we will be given some heat which is coming to this. Yeah, so there will be Q given. So when we assign Q, we will define. So there are two things: either you will have a temperature or the gradient given, right? So either Q given. So if you say point node number 1, node number 2, or maybe not even node 1 and 2, because we are just studying the equation right now. But you have x equal to 0, x equal to L. At x equal to 0, the heat coming to the system may be defined or temperature itself defined. So it may be given that, for example, this is example boundary conditions. T at x equal to 0, maybe T naught given. Yeah, and Q. Yeah, so Q at x equal to L may be given sub Q naught. So when you say Q, what is the meaning of Q? Q is energy coming or heat. Heat coming or entering the bar per unit time. So it will be in form of watts basically. Yeah. Where Q, we have to define terms of that. So already if you apply the Fourier's laws, and we know that Q flux is given by minus K dt over dx. This flux Q has watt per meter square. Yeah. This Q will have watts per meter square because this is a flux, right? So and this Q is different. This Q is multiplied by, so this big Q is actually area multiplied by this Q. Yeah, so what you are giving is minus Ka dt over dx is the big Q. So that means you may give boundary condition in terms of this quantity. Of course, you know that this will be essential boundary condition, this will be natural boundary condition. Yeah, so this is similar format. Essential boundary condition, and this guy will be natural boundary condition. And it can be at the either boundaries. So you can define this here, you can define this here, you can define both the things here and here as well, meaning that you can have a temperature here, temperature there, and you want to find out how the heat being conducted. Okay, so in order to find out the differential equation that we are going to solve, now we know that we have to proceed with taking a slice of length dx, and we are going to analyze it. Okay, remember that the surface is insulated. Okay, so there is no heat transfer going on from the surface. So we can, make sure that you understand, we will quote it like this. We will say that there is an insulation. So no heat transfer happening from the circumference of that, from the outer surface. Only heat transfer will be through this and these boundaries only. So there are two boundaries only. This is the boundary and this is the boundary. We will later on, when we study the 2D or 3D system, then we will consider this one. Then we will know that how to incorporate this. Okay, but not now. This is 1D system. So only in X direction, only the heat is flowing. Okay. So insulation. So actually, we are not considering anything here. And what do you have? You have some heat which is coming here, right? So we can write here Q is coming, right? And then what happens? Whatever heat coming here, there will be going outside here, right? So this will be Q plus dq over dx. Okay. So this is the heat which is entering here. This is the heat which is leaving it. There may be a heat source S. So introduce S, heat source S X, sorry, S is a function of X, heat source, which will have heat generation per unit time, per unit volume. Yeah, so this is a body equivalent of body force in the 1D elasticity problem. So this will be watts per meter cube. Yeah, so this is a heat source given like that. So there is a S here. And what do we have to calculate? We have to, what is the principle you applies here? Conservation of energy. Of energy. Why? Because we know that this is a steady state problem. A steady state problem, okay, meaning that with time, temperature distribution is not changing. Steady state means Tx is not changing. Yeah, so it has reached the steady state. That means whatever the expression of Tx is will remain there. Okay, so Tx is not changing. Okay, if means it is not a function of time. It is not changing with time. T itself is changing as a function of x, but not as a function of time. Got it? Okay. Now, looking at this equation, what do we get? We get like this. Total heat is conserved, right? That has to be equal to, so whatever comes has to go. That really means, yeah, total heat coming to the system equal to total heat in the, or you say there is a no increase of heat, right? So rather than writing like this, total heat not increasing with time, right? With time. Why? This is same as saying that this steady state. Yes, why it is like this? This is a steady state. So temperature is not changing. The heat content of this is also is constant. It is not changing. So heat not increasing with time. So what do we get? Q is the one which is coming to the system. So we write Q. This one is the one which is leaving the system. So we will write minus Q minus dQ over dx. This is the heat source, which is also the heat coming to the system. So plus S times dx is the length. So dx multiplied by, okay, so here heat source is given typically as a like energy per meter cube, but this is linear system. Okay, so here we defined, so S in this case, S in 1D system is typically in watts per meter kind. This is distributed, right? So it's watts per meter. So we will take that only, because 1D system, instead of taking this, we will take watts per meter. Sorry. We will take it as watts per meter. Okay, that means whatever this was, you multiplied by area, that will give you this S basically. Yeah. So in 1D system, we will take watts per meter. For 2D system, we will take watts per meter square. For 3D system, we will take watts per meter cube. So here watts per meter system. So you just have S multiplied by dx is the heat source, total heat coming to the system, and how all of them has to be equal to 0. Yeah. So finally, what do we get? You see that this and this will cancel out, and we have this plus S is equal to 0. Both of them have dx as common. Dx is not 0, so this we will get rid of. So finally we get this plus s equal to 0. So we get minus dq over dx, right, plus s as a function of x equal to 0. So this is what the equation of heat conduction. Yeah, and this is coming from the conservation of energy principle. Yeah, now we have to work on the details. So what is q? You have to find out now q, and for that we apply the Fourier's heat conduction, and you know that q equal to, as we discussed, equal to minus k, then a, right, and then dt over dx. All right, and same thing we will put it here, right here. So we get minus dq over dx, sorry, minus d over dx, and minus ka dt over dx, right, plus sx equal to 0, or you get d over dx ka dt over dx plus sx equal to 0. So this is what the equation of heat conduction is. Any question, guys? This you should know already, probably from other courses, from heat transfer courses on all. Still we derived it here. Okay, so that those coming from other departments may know about it. Okay, the background. So unless you know the origin of equation, you will not know what assumption we made and all. Okay, so that's why it was important. Yeah. So any question here, guys? Okay, now only thing is now boundary conditions. And boundary conditions, it can have various. You have, you can typically you have the, what you call is essential boundary condition. And in that case, you apply temperature. You can say examples are, you can have examples. You can have T at x equal to 0 equal to some value T naught, or T at x equal to L you can have at T some value TL, let us say call like that. So this is as a boundary condition. You can have natural boundary condition. The examples will be as you have Q, you make equal to 0. So what you can do is, so earlier we looked at and we say this is insulated. You can also do that this is insulated, right? You can make one end also insulated. Yeah, so example, the insulated boundary. So in that case, what will it will be? Insulation, this Q has to be equal to 0, right? So you can say that Q at x equal to 0 equal to 0. There is no heat transfer there. There is no heat coming, or neither coming nor going. Yeah, and accordingly you can write minus Ka dt over dx at x equal to 0 equal to 0, you can say. Or you can have constant heat source at the boundary itself. Yeah, so in that case you can also write Qx equal to 0 is equal to Q naught, or that really means you can write as minus Ka dt over dx at x equal to 0 is equal to Q naught. is you can also have the same thing at x equal to L as well, right? So you can write that way. So this is the natural boundary condition. Yeah. Any question, guys? Okay, you can also have the condition of convective heat transfer in terms of boundary conditions. So let us say you have T infinity as the ambient temperature, right? And whatever the T here is, there will be accordingly the heat transfer. So what kind of boundary condition you can write here? So if you have to apply here the convective heat transfer here, right here at this surface, then you will say Q is equal to, how do you write? Q equal to, you write minus H dt. So typically you have like this, Q equal to H times whatever the temperature at the end. So temperature at the end is L. Yeah, so you will have T. So Q typically you write in terms of what is entering, right? Remember that. Yeah, so what is, okay. Whenever you are talking about that, the one thing I think I should mention here, that when you write Q, you are giving the boundary condition on Q. So Q, you are writing minus K, right? Then you say A dt over dx. You have to make sure the sign here, okay? So always think about the sign, okay? How? So remember that when you say minus sign, to make sure that the heat flows from higher temperature to lower temperature. So if temperature gradient is negative, then only the heat will be flowing in x direction. Otherwise, it will flow in the negative x direction, right? So meaning of here, Q is positive here. This Q, whatever you are writing, is positive only when the heat is flowing in this direction. So if Q is positive at this end, that really means the heat is entering the system. If the Q is positive is this end, then heat is leaving the system. Yeah. So that really means what? Here, if you want it to, if we want to denote it that it is entering the system, then the minus sign will not be there, right? In that case, we will want the temperature gradient to be positive. If the gradient is positive like this, then only the flux will be this direction, because temperature is higher here, temperature is lower here. So because of temperature gradient, the heat will flow this way. Yeah. So if we, similar thing here, what we want is Q. If you are defining Q, it should go, the heat should flow this way, right? And this is flow only when TL is higher. So that means TL minus T infinity. So this is the what is called what it is called the convective heat transfer boundary condition. What we have is T, whatever T is at x equal to L minus T infinity, which is ambient temperature, multiplied by H. H is called the convective heat transfer coefficient. Yeah. And here depending on the its units, okay, if it is given as per,
Pardon, sir. Sir, pardon.
yeah.
So there should be an area, HA, area, sir.
So
Area
that's
is also.
that's what I'm going to say. Okay,
Okay,
so
okay. I'm sorry, sir. I'm sorry.
yeah. So depending on its units, either you have to multiply it by area. If for 1D, it's also possible that area is already multiplied, right? The way we do in the conductivity as well. Yeah. So heat conductivity also, either it will be given in terms of per unit area, or it will be in terms of like per unit. Okay, so we will talk about the heat conductivity, and similarly in the case of convective heat transfer coefficient, also it will be the same way. So if it is in terms of per unit area, then you multiply it by area. If it's not, that means it's absolute, it is given, then you do like that. But typically you have to multiply it with area, right? The way we did for conductivity as well. Got it?
Okay.
So you have to see basically the parameter, what kind of parameter is given. But you will typically see that the units will change when you go from 1D to 2D. Yeah, 2D is a 3D, because it's automatically taken care of, so that I mean, it's already known basically per unit area what is this coefficient. So sometimes you multiply by area already when you give in the problem. So you will see the problem in differently. So always look for the unit, what unit it has given. So this will be typically how it will look like. Yeah. Here it is complicated, because if you see here, what it's talking about is you have to temperature itself, which is a variable that we don't know what is the temperature here. Yeah, and on that there is a condition applied. Yeah. So accordingly you have to, so it is not saying that TL, it is not saying that TL equal to T naught or some value. It is saying the difference of that multiplied by this is something else, right? So writing it will be differently. Got it?
And sir, what is T infinity?
T infinity, ambient temperature. So in convective heat transfer, what happens? Convective heat transfer is it depends on the ambient temperature, right?
Sir, I
Got
am
it?
not from the. Sir, I'm not from mechanical engineering, so I don't know what exactly is ambient temperature. Like we understand it like air temperature only, and
Yeah, okay.
I mean
So
I
heat
don't understand.
transfer there are three types, okay? So one is it can be through the conduction, right? One is through the conduction. Conduction, as we are talking about, if there is a bar, and then maybe let us say this thing, yeah. So maybe I write here also. So conduction, one is conduction that we are talking about. So heat will flow through or conducted through the anything, like any of material. Second is we call it convective heat transfer we are talking about. In that case, what happens is let us say what happens, like in case of motorcycle, for example, right? And you have fins, you will see that at the engine, you typically have so if you can see, right? Motorcycle, what do you see? You see like if there's some engine, there will be this kind of structure given, fins. Do you see that? Do you recall?
No, sir, not recalling actually.
No?
Not
So,
not no, sir.
okay. So basically how it works is, so you have a surface, and because of the like flow of wind, for example, right? So like anything, you have to say something is hot, right? And you put it like food is hot. Then what do you do typically? You put it in the plate and you start the fan. Yeah. And what happens
Yes, sir.
because of that? This cools down. Yeah. So
Yes, sir.
this conduction, this what you call it, convection. Yeah. So this is like you increase the surface area, and because of the ambient temperature, and depending on the coefficient will change. If the wind speed is more, the coefficient will be more, and so on. Yeah, it comes from, so just a fluid flow is typically the fluid flow also comes into picture. So when you calculate H, the H value comes from various things. That comes from the fluid flow, the velocity of the wind, and all kind of thing. So and typically, if you have water, for example, to cool it down, so again the H value will be different. Yeah. So this typically because of the flow of the fluid. Yeah. So if the fluid is flowing
So
fast,
if it's
because of that,
something like
the heat will be what? Something like?
okay, sir. No, sir, I was thinking like it is
No,
something like evaporation. We can say a physical process like that. Although it is,
no,
yes, the
evaporation is,
mechanism is completely different, but we can compare it.
yeah, it is different. See, I'm showing the motorcycle. Let us say I'm very badly drawing. Okay, so let us say this is a motorcycle. You have like here,
Yes, sir.
and then
Yes, sir.
typically at this place, you will see there is some fins. You know, some engine is there.
Okay.
You have the engine
Yeah,
here, right?
yes.
So yeah.
Yes, sir.
So
Yes.
where you have the piston and all, so right there you will see this kind of structure. So very fine surfaces, so that is to cool down the engine. Yeah, the air cooling basically. Or you must have seen some ICs or transistor, right? So let's say transistor like this. You will have transistor here, and you will also have a material, some metal here. Have you seen? There will be some metal here like this attached to this. Yeah, and
Yes, sir. I
yeah. So
can.
this is transistor. Yeah, yeah. So this is for convective heat transfer only. So what happens because of the and there will be a fan. You will also see in the in every computer there will be a fan which will what will do, it will induce the flow, and because of this flow this will cool down, right? So the energy will be transferred from because of that. So because of the flow it is going out. So this is as a this will be as an example of the convective heat transfer. Yeah. So and this is going because of the ambient temperature of the wind, of the air which is flowing here. Yeah.
Sir,
Got it?
can we
But
compare it like
coefficient
to
will be
the forced? Sir, can we say it like a forced conduction?
it's no, I don't say force conduction. It has different principle. It is because of the flow of fluid around it. Yeah. So it has you can say in a way force, you can say it that way. Yeah. But mechanism is different. Yeah. Anyway,
Yes,
for
sir.
you it's
Yes.
mathematics. Okay, for if you want to understand the physics, then please read or do that course.
Yes.
Okay, so anyway, here the idea is not to understand the physics and go delve into it. For you this is given, right? This
Yes,
this is another boundary condition, another mathematics term, and it tells you that this is the expression, this is the how the heat is being lost, or you can also gain the heat as well. If the temperature is low here, then this can increase. Yeah.
Yes.
Got it? And third heat transfer is the radiation, but radiation is quite non-linear. T to power 4, you remember sigma T to power 4 kind of, so Q equal to sigma T to power 4. So this is radiation is non-linear, so hence we don't apply here, because all this problem what we are solving here for the linear problem only. Okay, got it? Okay, so you can just see Wikipedia and all. Okay, so you can see the what is convective heat transfer, and Okay. Important thing here there is only that heat transfer is given like this expression, where H is the one coefficient, and then temperature difference it works on. Temperature of the surface where the heat transfer is taking place, and the difference of that with the ambient temperature is the one that plays the role. Yeah, so that's how it is. So for you is a mathematics anyway. This course is about mathematics only. We try to also teach some physics here so that you are not confused. Yeah, but if there is no background, then you just read little bit. That's it you require. Otherwise, you can take it as mathematics. Yeah. Okay. Any other question, guys? Yeah, okay. Okay. Then similarly, there will be a diffusion. Okay, diffusion. And in diffusion, what happens is this is a mass transfer. Right? So heat transfer, you call it mass transfer. So basically, what happens is it happens in our body. For example, a lot of diffusion takes place. Yeah. This very important thing. Like even when we uh, do like although there are many things are involved there, but across our the cell membrane the diffusion takes place. Then there will when we breathe goes to lungs, there is a diffusion there. So this kind of things it's there very important in biology. As such, you also it is very important in the computer industries, right? All the chips that are made, they are made of diffusion. How you make the semiconductors, they are based on diffusion. So this is a very important thing. And how it works like a heat only. It is actually equations are like heat. I mean, it is not different. How it works like what happens is as per there is a principle called the or law. There's a fixed law. Okay, and this fixed law says J equal to minus d we call it psi, or let's call it phi, or d we can say, or c also, dc over dx. So what is that? So basically J you call it flux. Yeah, and this is the actually volume concentration flux, or you call it flux. Yeah, so J is flux. We will understand what is the meaning of that. D is called diffusivity. Okay, and C is the concentration. So what happens? Concentration of any species, it could be ions. Yeah, it could be molecules. All depends. So it is like in one side, let us say you have concentration C1, at the other side C2. So you will see there will be a flux, means the concentration of any species. So flux of flow, basically there will be flow of the not fluid but the species we are talking about, either ions or any other thing. Okay. So here as per this you can write J, which is again how do you define what are the units? Units concentration, as you know, it will be in moles, right? Moles per volume. So moles per meter cube, it will be like that. Then flow again, it will be moles, right? Moles per meter square per unit time per second. Yeah. So rest you can find out based on this. You can find out what the units of D will be. But this is moles per meter square per unit time is the flow, right? This is also again a steady state. This is concentration, as you know, moles per meter cube. and accordingly d you can find out. So this is a fixed law. So similar thing we can do, like if you have, again, all the mass transfer is happening from in x direction only. The other direction is insulated. Here there is no mass transfer, so this is insulated. Yeah. In this case also you can write q term basically. So as I said earlier, there will be a q entering. This will be q plus dq over dx, where q is the, actually we are talking about the total flow. Yeah, so q is basically will be in terms of moles per second. Yeah, so this already multiplied by area basically. Yeah, so so this is equal to J times A, flux times area, right? Flux times area, then you get Q. So this we know means this is the relation. Okay, so this is how it is, and there will be, as in heat transfer, there will be a source as well. Yeah, or you call ion source or mass source. So now in order to analyze it, how do you do? We take the same one slice of width dx, and then what we do, we have this this slice we here, and we can have one q. Okay, so this one is basically we assume that time when we talk, I wrote dq over dx times dx. Basically, when it is very small, then only we can write. So anyway, here it is going out q plus dq over dx times dx, and then you have s here, and of course these two surfaces are insulated. Yeah, so this is what the equation, what we see, how the mass is flowing in and out, and this is being generated. Yeah, so this S is source. There could be source of ions, for example, right? So in that case, S is units will be moles per second. So much of ions being generated per unit second. Right? Typically, it will have per unit. In this case, per unit second, per unit per meter as well, because in 3D it will be per unit moles per second per unit volume. In 3D problems here, in 1D it will be typically per unit length, because this is the linear system. Okay, now how to this will be conservation of mass, means steady state. So we write here a steady state. Okay, so mass in the control volume, or this control element, right? Volume equal to steady mass in the is equal to constant, means it's not increasing with time, right? Constant with respect to time. So that really means we can work out here the equation. So this Q is coming to this system of control volume. So we have Q coming, so we write Q plus, then we have, because of this also the mass is entering to the system, so S, which will be a function of x, so we can, yeah, Sx multiplied by dx. Yeah, so dx, because this is per unit length, so dx. Then this is leaving the system, so we will have minus q minus dq over dx is equal to 0. Yeah, so means whatever is coming has to leave. That's what the meaning is. Yeah, so that the content remains the same. Whatever is coming per unit time is leaving per unit time. So content of this is same, and that really means you minus dq over dx plus sx equal to 0. Yeah. So similar kind of expression you got in heat transfer as well. So actually heat transfer and diffusion both are actually the same equation. Yeah, so you have this. Now next is you have the relationship Q equal to, we said J times area, where J is the flux, and which is given by minus d dc over dx. Yeah, and then area, so minus dA dc over dx. We will put this value in the previous equation here, and what you will get is minus, yeah, d over dx, then minus dA dc over dx plus sx equal to 0, or d over dx dA dc over dx plus sx equal to 0. So this is the equation. Okay, so what we see here is equation is similar to the 1D elasticity problem. You had here E and A, instead of C you had U, and instead of S you had B. In heat transfer problem, instead of D you had K, you also had A, instead of C you had T, temperature, and then here it was heat source. In this case you had diffusivity. Instead of the Young's modulus, you have the C, concentration, instead of the displacement, and you have S, source, instead of the body force Bx, right? This remains the same. All other boundary conditions you can apply. Yeah, so boundary condition will be similar to the essential boundary condition. So you can have C at x equal to 0 equal to C naught, or and you can have both C x equal to L equal to CL. You can have that, and then you will have natural boundary condition. Yeah, and in that case the Q value, you give Q at x equal to 0 equal to Q naught, or Q at x equal to L equal to QL. So you can give that. Rest, when you have to solve the same way. So if you have to find out the weak formulation for this strong form, you can do the same way as we have done for others, right? For the 1D elasticity problem. Any question, guys? So far so good. You can also add advection. Okay, advection-diffusion equation, all you also call it. And advection is because of the fluid flow. Yeah. So if there is a, okay, Shubham, I think the convective heat transfer, you can relate it as advection actually. Yeah, it is something like advection. Yeah, not
Yes, sir.
close.
Yes, sir.
Yeah, not exactly, but similar to advection. Okay. Now advection you will know, right? You are from civil, right?
Yes, sir. Little bit.
Okay. Yeah, so you are little bit from civil. What do you mean?
I can get it little bit.
Okay.
Yes, sir.
Okay. So advection is because of the fluid flow comes into picture. Okay. So this is because of the fluid flow. Is involved. So what is the meaning of that is, let us say you have 1D bar, not bar, but 1D pipe or sort of thing. And there is a fluid here, right? There will be some fluid which is flowing. And inside that also there will be some ions, right? Let us say you have Na plus and Cl minus kind, so some ions are there, but there is there may be the difference in the concentration. This is concentration gradient, right? C here will be different, C there here different. Then there will be a diffusion of these species, but at the same time, if you also have a V, the velocity, so V, the velocity of the solvent, right? So NaCl is solute. There will be solvent which is also moving basically. Yeah. So because of that, it will be a little bit complicated. And in that case, how will you find out? Well, the same you do for, so this is dx, control volume we will work on.
Excuse me,
And
sir.
yeah.
Sir, actually we have class at 11, so you're requested to kindly leave on time because last time we were called to join at time on.
Yeah, okay. Okay, man. So I will just give me 3 minutes, okay? Just 3 minutes, okay?
Okay,
Is
sir.
all right? Okay. So you have a Q here. You have Q plus dq over dx, and this is what is flowing, and then you have Sx, and then also you have a V. So if it is a C here, let us say if the concentration here is C, so what happens? You will have here C times V, right? C times V times A. There will be area as well. Yeah. So this is concentration here multiplied by V. So okay, multiplies the area. So concentration times this is length, this is area, so that becomes volume multiplied by concentration, that gives you the number of moles and per second, right? So it is same as Q, right? What it is leaving is will be V times A, and then you will have C plus dc over dx. So since one way of transport of these species is by diffusion, the second way is by the fluid itself. Since the fluid is flowing with velocity v, so it carries with it number of species depending on the concentration. So b times c times a will be coming, and b times a times c plus dc over dx times dx will be leaving. And now rest we can find out. So will be q plus cva minus q minus dq over dx minus va c plus dc over dx is equal to 0. Oh, sorry, there will be s terms as well, plus s times dx is equal to 0. Yeah, and if you work out, q will cancel. So what we will have is this one minus dq. So minus dq over dx term will be there times x. So x will be common here also. This and this will cancel out. What we get is this guy, right? This will be minus minus VA times DC over DX. So minus VA over DC over DX plus SX equal to 0. So this is the equation with advection. Yeah, and next will be, if you put Q, so that automatically makes it D over DX, D times A DC over DX minus VA DC over DX plus SX equal to 0. So this is the one which, this is called diffusion advection equation. Okay, guys, that is all. Okay, so rest you do the same way. You apply the same. You make it from the strong formulation. You go to weak formulation, and you do the analysis. That's it. Yeah. Okay, guys, I will see you tomorrow. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.